Hi everyone, so as always we start with the learning objectives. Here they are. Feel free to go through them now or go through them later when we're done with this. So magnetism is of course related to magnets, and it's very likely that you already know a lot about magnets, right? So you know that every magnet has a south pole and a north pole, and you also know that if I put a north pole and a north pole together, they repel, whereas a north pole and a south pole, they attract. You may know that if I place a little compass here, yeah, that's a pretty bad compass, the north part of the needle will point to the south of the magnet, and the south will point away from the south of the magnet. And that if I put this same compass on the other side, the opposite is going to happen, right? So the south will point to the north, and the north will point away. Now, these properties are extremely complicated to explain, so complicated in fact that it took quantum mechanics to solve them. In fact, not quantum mechanics, but the relativistic version of quantum mechanics. So imagine. So instead of starting by studying magnets, we're going to start by studying currents and the forces between them, and then we will use what we learned about them to explain magnets, even though we won't do a completely good job of it, as you'll be able to see later on. You probably are not familiar with this at all, but it turns out that if you put two wires together and make them carry a current in the same direction, they will attract each other. So this one will go this way, and this one will go this way. Now, this puzzled scientists a lot because, well, these are actually neutral, right? So what's going on? Why are these things attracting each other? And the only possible conclusion is that it's the current that's creating the attraction. Another really, really puzzling fact is that if you place a compass around this wire, the compass will always point in a way that goes around the wire. So imagine that the north side of the compass is following the laser pointer like this. And that was also pretty weird, because what do currents have to do with magnets, right? And we know that compasses are magnets, so why on earth would a magnet be attracted by a current? So this told scientists that magnets and currents were somehow linked. Now, in order to come up with some kind of explanation for this, physicists came up with the idea of the magnetic field. And what they said was, well, a current creates a magnetic field around it, and that's what makes the compass move. And they defined the magnetic field in such a way that the direction that a compass is pointing will tell you the direction of the magnetic field. So if the compass is pointing this way, and this is north and this is south, then the magnetic field goes this way, all around the wire. In order to see this easier, let's take a look at the wire as if it was coming out of the page. So imagine that this is a wire that you're seeing the cross-section of, and the current is coming out of the page and towards you. And this is creating a magnetic field around it. That is, if I place a compass here, or here, or here, or here, or here, it's going to point in a certain direction. So let me just show you. So for example, I have a compass here, and it turns out that the north pole will point this way and the south pole will point this way. And if I do it here, then it's going to look like this. So north, south. And hopefully you start to see a pattern, right? So north, south. It seems as if this thing goes around the wire. So the magnetic field seems to point around the wire in the direction that a compass points. And that's really what happens. A wire whose current comes out of the page will create a magnetic field that will look like this. And of course the direction will be the same as the compass was pointing. Now, luckily for us, there is a very easy way to figure out whether the magnetic field goes this way or this way. So if you know whether the current is going into the page or out of the page, then using a very simple rule called the right-hand rule, you can easily figure out whether the magnetic field goes anti-clockwise or clockwise. So let me show you by showing you a little video. First though, let me get rid of this. Alright, so yeah, that's my hand and that's my mouse cable. So as you can see, if my thumb is pointing in the direction of the current, and remember this has to be done with the right hand. If you do it with the left hand, it doesn't work. Then your fingers point in the direction of the magnetic field. Therefore, if I reverse the situation and instead I do this, then if the current goes this way, then the current will point this way around the wire. And sorry, I just made a mistake there. What I meant was that the magnetic field around the wire is given by your fingers, not the current. The current is, of course, given by your thumb. So what I would like to do now is to determine the magnetic field for a circular coil of wire. And of course, you need to imagine that this is actually connected to potential difference and that this is not really solid. So this should do something like this, right? This is a voltage between those. Now, what I will do is use the right-hand rule here to determine which way the magnetic field goes in this coil. So, okay, now you can do this yourselves, and I actually recommend that you do, but it's easy to see that the magnetic field goes into the coil and then around the coil like this. And if you do it all around, you'll see that this happens everywhere. So here the current points this way, so using the right-hand rule, you can also see that the magnetic field goes into the coil and then comes out this way. So you can see that magnetic field goes into the page and then comes here out of the page. Now the cool thing about this is that I can get many coils together like this, and then they all will do the same, right? That the magnetic field will go into the coil and then out of the coil. So they will reinforce themselves so that we have a very strong magnetic field inside the coil and a not so strong magnetic field outside. And before we go to the next slide, I would like you to stop and think, does this look like the magnetic field of anything you know? So remember that the magnetic field shows us the way that a compass would point if placed there, right? So this field is telling that if I place a compass here, it will point this way, and that if I place a compass here, it will point this way. So does that look like anything you know? And if you said magnet, then you hit the jackpot, right? As you can see, it's exactly the same. So a solenoid, which is this thing that's made out of many, many coils, let's just write it down here in case you want to know the name of this. This is called a solenoid. Has a magnetic field that looks exactly like that of a magnet. And that should make you think, why is this so? What's going on? Why do magnets act like solenoids? Why do solenoids act like magnets? And the answer is a little complex, but it's related to some really, really, really tiny currents happening inside the magnet. Unfortunately, answering this requires us to know a little bit of quantum mechanics. However, I think this is relatively easy to explain, so I'll give it a shot. So, as you know, inside of every atom, there's a bunch of electrons, right, which are negatively charged particles. And these electrons are just spinning around like crazy. They're just going like that. Ooh. Now, on top of this, these electrons are also spinning around themselves. So imagine that this is an electron. Then this guy can be spinning around itself like this, or the other way around. And it turns out that because of some subtleties in quantum mechanics, it's only allowed to spin one of these two ways and at a very fixed speed. That is, its spin can only be this or this at a fixed speed. It only has two possible states of spin. And because it's about spin, we call this the spin of the electron. Oops. And then you may have heard that spin can be either 1/2 or minus 1/2. And all this means is that, well, in this case it's spinning this way, in this case it's spinning the other way around. Now, because this is a moving charge, this acts exactly like a coil, right? One of those coils, and therefore there should be a magnetic field that goes around this. So each electron behaves like a tiny magnet. But if each electron behaves like a tiny magnet, then why don't we see every single material in the world be magnetic? And this is related to the fact that most materials look like this. So we have a bunch of electrons, and I'm going to, instead of drawing the spin, I'm going to draw a little arrow with the direction of their magnetic field. So this one's pointing this way, this one's pointing this way, this one's pointing this way, and as you can see, they all have different directions, right? So what happens when I average out all of these random directions of the magnetic field of the electrons? Well, that I get 0, right? Therefore, I wouldn't expect most materials to be magnetic because the magnetic field of the electrons cancels each other. But what if I can manage to do this? So I take all my electrons and some way, for example, by using a magnetic field, I manage to get all their spins pointing in the same direction, or at least I managed to get a substantial amount of their spins pointing in the same direction. Now they don't cancel each other out anymore, do they? So what I have is a big number of coils whose magnetic field is all pointing in the same direction. Now if I look at this macroscopically, so this is in a substance, what I will see is a magnetic field that goes into it and out of it, just like a magnet. And of course it's just like a magnet because it is a magnet. So until now, we've been focusing on the magnetic field. But what we would really like to know is the force that is exerted on a current-carrying conductor. And in order to do this, we need to realize that even though the magnetic field of a wire goes around the wire, the force actually points towards the wire. And now this is really weird, right? Because look, the force is perpendicular to the magnetic field that goes into the page, and it's also perpendicular to the current that goes this way. This does not happen with the gravitational field at all, or with the electric field. This is completely different. Now, in order to understand why this happens, you would have to know a lot of relativity. So don't worry if this doesn't make any sense to you. That's just the way it works. And when you know a little bit about relativity, I will be able to explain to you why these really bizarre effects take place. But for now, we want to focus on how do we find out the direction of the force if we know the magnetic field and we know the current. Well, there's many rules for this, but I'm going to use this one that looks very, very simple. Now, as you can see, the knuckles point in the direction of the current. The fingers point towards the magnetic fields, and then the thumb points in the direction of the force. By using this rule, you can always figure out where the force is going. Another really easy trick is just knowing that if two currents are parallel, then they have to attract. If they are pointing towards different sides, then they will repel. And this will instantly give you the right direction for the force. Now, of course, since this is physics, we would also like to know the magnitude of the force, that is the number, right? So how strong is the magnetic force that this wire is exerting on this? And if we know the magnetic field, it should be something like we did in the electric field, where remember that force was Q times E. But in this case, we don't have a charge, right? What we have is a current. So the current is our charge. So we would expect something like force equals intensity, or current, times B. However, that's not entirely accurate. That would happen for each piece of wire. But the thing is, the longer the wire, of course, the more the force, right? Because this part is going to be receiving a force, and so this part, and so this part, and so this part, and so this part. So this tells us that the force has to be proportional to the length of the wire. And then we get the final formula for the force on a wire, which is length times current times magnetic field. And of course the direction, you can find it using the other right-hand rule. To determine the magnetic field on a charge, we can do exactly the same thing. So In this case, the charge is moving this way, so this is its velocity, and this is the equivalent of the current, right? It's the same thing. It's just instead of having many particles, we just have one. And then the magnetic field is going into the screen. So imagine this is 3D, and this really goes in. And this is drawn in perspective. And then using the same rules before, so here are knuckles, here go our fingers, and then the thumb shows the direction of the force, which should be this way. So again, this is B, this is V, and this is F. Now, to determine the magnitude and the force, we will think about it this way. Remember that for a current carrying conductor, the force was L, I, B. And now we look at this, and we're like, well, we can imagine this particle moving as the intensity. And in a way, the more the charge, the more the intensity, and the more the velocity, the more the intensity. And in this case, there's no length involved because this thing is just moving this way and length is 0, right? So knowing this, we can just write down the expression for the force on a charge that's moving in a magnetic field, and again, it has to be proportional to the charge, to the velocity, and to the strength of the field. And this is the expression for the force on a charge that's moving with speed v in a magnetic field. Now, so far we've only seen examples where the velocity and the magnetic field are perpendicular. But what if they're not? So what if the velocity has a certain angle with the magnetic field? So this is the magnetic field, and the velocity, instead of pointing this way, points this way. Then we seem to have a problem, right? So to see what to do in this situation, what I'm going to do is just draw the velocity in the magnetic field and figure out a way. So imagine that this is the velocity, and this is the magnetic field. So B, V, and there's a certain angle theta between them. And the thing here is that we're only interested then in the component of the magnetic field that's perpendicular to the velocity. This is the only one that's going to have any effect. Now, if you know anything about angles, you know that theta plus this angle here, let's call it theta prime, has to be 90 degrees. So if this is theta prime, we know that theta plus theta prime equals 90 degrees. And we also know that the perpendicular component of V, this one, is the projection of this at this angle, theta prime. So the perpendicular component of B, let's just call it B little thing, it means perpendicular, is equal to B cosine of theta prime, which is of course equal to B sine of theta, right? Since theta plus theta prime equals 90, this has to equal this. So then what do we do? Well, if, for example, the intensity or the current and the magnetic field are not perpendicular, we only get the perpendicular component of B, which we obtained by multiplying B by the sign between the current and the magnetic field. If we want to obtain the force on a charge, where V is not perpendicular to B, again, instead of just having B here, we have B sine theta, where theta is the angle between V and B. So let me just rewrite this then. The force on a current carrying wire becomes L I B sine of theta, and the force on a charge becomes Q V B sine of theta. And now we have a formula that works for every single possible case. So far we've been talking about forces on wires if there's a magnetic field, but we haven't talked about the strength of this magnetic field. And we know that this wire creates a magnetic field around itself that looks like this, but we have no idea how strong this field is. And what I would like to do now is try to deduce a way to calculate this field. Now, there's one way to see this, and that this is infinitely long, so the magnetic field strength is really getting distributed through bigger and bigger circles, right? So it's not like in the electric case where you had a charge and then the strength got distributed over a sphere, this is distributed instead over a circle, over the perimeter of the circle, right? So in a way we could think that the strength of the magnetic field has to decrease with 2 pi r. And indeed, that's what happens. So the strength of the magnetic field created by a wire is, well, first it's proportional to the current, so has to be I, then divided by 2 pi r, and then we need a proportionality constant here, as always. And in this case, the proportionality constant is called mu 0, where mu is the Greek letter mu. Now it turns out that this mu letter has a value of 4 pi times 10 to the minus 7. So what are the units of this? Well, it turns out that we measure the magnetic field in these units called Teslas, and we write them down with a little t. Therefore, it follows that the units of our magnetic constant, which actually is called magnetic permeability, have to be, if we want B to have unit of Teslas, Teslas meter divided by ampere. And it's really easy to check that this meter cancels with this meter, these amperes cancel with these amperes, and we're left with Teslas, which are the units for the magnetic field. What we would now like to be able to know is what the magnetic field of a solenoid is. And remember that the solenoid was this thing that looked like a coil, and there's a certain current going through it. Now, in order to do this, first we need to know the magnetic field created by a loop of wire. Unfortunately, in order to deduce this, we will need to know some calculus, which is not the case, so you will just have to trust me and believe that the magnetic field at the center, and outside we're not concerned about that because it's much more complicated. The magnetic field at the center is equal to mu 0 times the current divided by 2r, where r is the radius of the coil. Now, even though I can't prove this to you, this kind of makes sense, right? All the field lines are inside here and they have nowhere else to go, so the field should be constant in here. Also, of course, the bigger r is, the more separated the wire is from here, and therefore the less the field, and the more the current, the more the field. The factor 1/2 and the absence of the 2 pi r are a little harder to explain. Now we can take a look at the field in a solenoid. So remember that in a solenoid we will have a certain number of coils, let's call that N, and we will have a certain current, let's call that I, and the solenoid will have a certain length, let's call that L. Now, of course, if the solenoid had length 0, it would mean that all the coils are in the same place, so the magnetic field of the solenoid would just be adding up the fields of each coil, right? So it would be this times N. But that's not the case, because in reality, this takes up a length L. Now, again, and unfortunately, I won't be able to prove this to you because we would need to know some calculus. But then the field of the solenoid is given by mu 0, again, N, which is the number of coils, times the current, and that makes sense, and then divided by L. And in a way, this also makes sense, right? Because if L is very small, it means that all the coils are concentrated at the same point. So their field would add up and would become a lot stronger. But if L is greater, then this means that the magnetic field gets more spread out, and therefore we would expect to see less magnetic field at each point in the coil. Now, I leave you again with the learning objectives. Remember, this is a very abstract part of fields. If you still feel confused about what a magnetic field is and what it does exactly, don't worry too much about it. You're not supposed to understand exactly what it is. nobody does until they do relativity. So just for the moment focus on being able to calculate things with it, being able to find its direction, and we will focus on understanding what exactly it is later on.